Hello and welcome back to Calculus 2 for one last time. This is it, right? We're talking about polar coordinates, calculus in polar coordinates, and the course is over. Now this is going to set up the mood for Calculus 3. Polar coordinates are used a lot in Calc 3, and then they're also upgraded in 3D. What you build on top of polar coordinates are cylindrical and spherical coordinates. So this will be used and upgraded in Calc 3. Now, before we go and talk about polar coordinates, I want to first talk about rectangular coordinates real quick so we can draw the differences between the two worlds. So rectangular coordinates, a graph x and a y. When you pick a point, x, y, the way to get to that point is to count x amount of units along x-axis and then go 90 degrees up or down, depending on which way y goes. And you can do that, or you can go y along y first and then x. And what you see is whatever path you take, it will get you to x, y, and it always creates a rectangle. Therefore, these are called rectangular coordinates because they create rectangles as you go around. And all of your mathematics so far was done there. Didn't work very well with a circle, right? Because circle was rounded and equation for the circle is not a function, so we could not integrate, we could not do anything easy, right, with a circle because it was not a function. Even derivatives for circle, right? If you want to integrate, find the area of the circle, you set up your equation and you usually set up a quarter of a circle and then times 4. And when you're integrating that quarter of a circle, you had to use trigonometric substitution. So it was double annoying, right? Well, polar coordinates are supposed to fix that because polar coordinates are supposed to give you the way to operate in with rounded objects and even help you with the fact that they are not functions. So when we are talking about these guys, these were your 2D rectangular coordinates. And you also had y equals f of x, where x was your input and y was your output, and you had all of the calculus you learned so far, Calc 1 and Calc 2, done right there. Now we are interested in polar coordinates, and those are r, theta, where r is the radius and theta is the angle. These coordinates live in the same xy coordinate system, but the way to get to the point is different than what you had so far. So if your point here is r, theta, the way you would get there is you would draw the value r, and then you would swing that one around to hit whatever angle theta you have. So, and then you would get to the point r theta. So to give you an example of this, we can take a look at, let's say, 3 and then pi over 3. So 3 pi over 3 is going to be we have a pi over 3 angle, and then I'm going to draw 3 on my x-axis, and then I'm going to take a compass and just swing this into the line, and this location here is 3 pi over 3. This is still only XY graph. It's just the way to get there is different. We used to go along x-axis and then up or down on y. Now we go along x-axis again, and then we swing to meet the angle that it's given to us. Let's take a look at -2 pi over 6, let's say. My r is negative now, which means that I will draw this way to -2. And I still need to do the positive angle pi over 6. So which way do I go? Do I go from -2? Do I go above or below for positive pi over 6? Below. Because the positive angles are always counterclockwise. No matter what, your positive angles are always counterclockwise. So you will swing down to get to your -2 pi over 6. So now I can create like a diagram or something. You want to think about it as a formula sheet or whatever to graph all of the points. You will draw positive r's this way, negative r's that way. You will have your positive thetas and your negative thetas, and over here your positive thetas and your negative thetas. If you want a single concept for angles, just think about that this way is always positive theta is always counterclockwise, and the negative theta is always clockwise. You can see that clockwise motion on blue arrows is always negative theta. So there you go. That's it. That's the way to graph the polar, and we are still on x and y, so that doesn't change. And now, because we know that we are still on x and y, we can come up with the conversion between the two worlds.
They have this in pre-calc a little bit. This seems familiar.
That some professors, teachers do cover this, which is great. But our first lecture, 12.2, is just pre-calc, and the second one is calc. So to graph, r theta. Oops. All right. So now, conversion. If you think about the situation, you have your point on the xy graph that you know now can be represented as xy or r theta. And when you label this triangle, with all of its features, you can write 4 formulas that will give you conversions between the systems. If you write cosine theta is equal to adjacent over hypotenuse, which is x over y, you will get, x over r, you will get that x is equal to r cosine theta. If you write sine function for the same picture, you get y over r, and that gives you y equals r sine theta. And these two together create a conversion from polar to rectangular, because common sense, right? You have r, you have theta, and you are computing one at a time. You compute x first, then you use the same r and theta to compute the y. So that has to be conversion from polar to rectangular, because for each one of the dimensions of rectangular, both polar are given to you. If you write tangent theta, you get y over x, and from there you can come up with that theta is equal to inverse tangent of y over x. And the last one is the Pythagorean theorem, where x squared plus y squared equal r squared, from where you can solve for r as the square root of x squared plus y squared. And this creates the second set, which is rectangular to polar, because you see that you are given x and a y, and you compute polar ones one at a time. So these 4 formulas are your conversion factors between the two worlds. Sometimes you have to convert, right? Now the question is, do these systems compete, right? Why would we bother having one or the other or both if they're both on x, y, if they're both representing the same point, and so on? And to answer that question is simply no, they do not compete. What they do is they complement each other. And you are going to see very quickly that what's beautiful in one system is absolutely disgusting in the other. And that's the reason why we study them both. And you will see that very, very quickly, but let's just convert a point. So we'll take a simple point, say, 8, -3, which is in x and y, and you want to convert that to polar. Well, you can convert, you need r and theta, right? So r is equal to square root of 8 squared plus -3 squared, which is square root of 64 plus 9, which is square root of 73. Yeah, good luck with that, right? So your r is square root of 73. And then theta is even worse. It's inverse tangent of -3 over 8. You see that? So a point that is 8 -3 in rectangular world works out to be exact root 73 comma inverse tangent of -3 over 8. Yeah, you can get the degrees and stuff. Generally in mathematics we like radians because formulas don't work with degrees. So that's why we like pi over 2 and all of these things, because your arc length formula, let's say, right, where S is equal R times theta, that one only can take polar. Your graphing calculator must be always in radians in order to show the graph if you have trig involved and all that kind of stuff. So now what we see is that this 0.8 negative 3 converts into this monstrosity down there. And that's what I said, that when something is beautiful in one system is going to be disgusting in the other. Let's take a look if opposite is the same. So how about if we have, I don't know, 3 and negative pi over 6, let's say. Well, that's nice and simple to deal with the polar coordinates. You just draw 3 units on the x-axis and then just go down 30 degrees, right? Pi over 6. So it's very simple for us to understand where the point is and how to get to it. But now you want to convert that to rectangular, because you have nothing better to do. Okay, x is equal to r cosine theta. That's what we learned in a red box up there with the conversion factor. So r is 3, and we need the cosine of negative pi over 6. So that's 3 times root 3 over 2, and you get this wonderful coordinate for x, and then y is r sine theta, which is 3 times sine of negative pi over 6, which is negative 3 times 1/2, which is negative 3/2, and the point you are looking for is 3 root 3 over 2 and negative 3. Yeah, right? So really no good. The only point that converts nicely is 0, 0, right? 0, 0 converts into 0, 0, so yay, right for that one. But everything else has this behavior where if it's beautiful in one system, it's not going to be so nice in another. And that's something that is going to be preserved for the rest of the section as well. So once you understand and know how to graph a point, the next natural stage is to think about the function, right? So now we want to see what is happening with these polar functions. And in this case, right, we are going to have, so let's go with the polar functions. We are going to have r as a function of theta. So angle is the input and radius, the length of the radius, is the output. Now this is going to lead to some very interesting types of functions. Say, what happens if I have function r equals theta? We just want to consider this one. And you should start by graphing the function, and we do that the same way like we do it in rectangular coordinates, what we did in middle school as well. You pick your thetas, you compute your r's, and then you plot the points you get, and technically that's it. Now, we don't get to pick, right, 1, 2, 3, because 1, 2, 3 are not going to work nicely for angles. What is the angle of 1 radian? Generally, people don't know, or 2 radian or 3 radian, right? We like pi angles. So, to graph this, I'm going to create a chart of values where I'm going to pick my thetas and compute. You know, let's do 2 theta. Let's switch the function to 2 theta to make it nicer. Can anyone try and guess what kind of function are we going to get here? What kind of line? Spiral. Very good. This is going to be a spiral. Awesome. Because as your angle, right, they're going to start at 0, 0. That should be clear, right, for everyone. They're starting at 0, 0 because when you pick theta equals 0, 2 times 0 is 0. So it's going to start at the origin. And then when you start picking out angles, right, as you start going around the circle, the radius is going to start getting bigger, and it's just going to trace the spiral around. So the values we want to pick, let's say pi over 4, pi over 2. Let's go with a pi, 3 pi over 2, 2 pi, right? Stuff like that. So now I want to graph this. Now each one of these will be doubled. Now we know that pi is 3.14, so this is 3.14 over here, this is 6.28. Pi over 4, so that will be 1.57. These are the values for your r. Now, with your scale in centimeters or inches or something, you get to measure these values. Now, I do have these little squares here, so I'll just follow the squares. I start at 0, 0, and then at pi over 4, which is in this line here, I need 1.5 units. 1.5 units is about there. One and a half units. You go that way. Pi over 2 is 3.14 units. It's right here. And then at pi is 6.28 units. So 1, 2, 3, 4, 5, 6.28 units. And if you connect these dots, you see that the graph goes here, then up there, and up there. It's going to go like that. And it's going to create a spiral that is going to go around. So this is spiral. So now you know mathematical equation for spiral. Next time someone tells you, what do you know? How about the equation with a spiral? And there will be opportunity for you to also explain the polar coordinates and the rest of mathematics along with it. So.
The rest of all of them?
Yeah. Now remember, I mean, you're learning this in Calc 2, so at least you have to explain everything up to this point. Nearly 11 chapters of stuff. I can skip a sequence series. We don't really need that. So how about 9 chapters of stuff? Sounds good. And then by the end of that talk, and that's why we have polar coordinates. So that's what I know. That's that's how this stuff is done. I mean, All right, cool. The question is, what else do we get? And for that, I'm going to use the calculator now to show you some of the graphs and some of the functions, right, that you can get. Just going to get this. I hope that this camera is not mutilated to the point where it doesn't work anymore, because every time I come in, there's some kind of sculpture going on. Is it working? It appears that it's working. Document orientation. Okay, good. Oh, this is working so well. You're gonna love it. Look at that.
Can't you just do it on decimals? Oh wait, no, this is for electric, right?
Oh, this is even better. If I turn off the light.
Gotta hit it with that like obscure light. Just nice.
Oh, it's. I got there. I just need to work my magic with light. Let's see. Actually, you know what? I'm just gonna turn it this way. There we go. I think, yeah, there we go. Perfect. Look at that. And now we're going to make this full screen so it's even worse.
The frame rate is atrocious.
Then we're going, frame rate is -7.
What is going on?
No, I'm telling you, man, it's high tech, right here. And when I turn this, awesome, it works, good. Okay, so the first thing you have to do with your calculators is to make sure your calculators are in polar, which is POL, and in radians. Your calculators can graph parametric equations, which is what we learned in 12.1. And your calculators can also graph sequences, which is the last one over there. So you have your regular XY functions, you have your parametric from 12.1, and your polar from 12.2 and 12.3, and then sequences going back to 10.1. So this is what your window should look like for I think he just got possessed. Sharp.
Yeah, that is.
All right. Good. So that's your first step. Now, once you go now to the screen y equals, as you can see, it now shows R1, R2 instead of F1, F2. So, because now it's looking for a polar coordinates input. What I'm going to do is I'm going to push 4 cosine 4, and now when you press the variable x, it is going to print theta, because the variable x has also t, theta, and n on it. And then I'm going to go in, so push enter. And then I'm going to go into window, and I'm just going to make x to be -6 to 6, and y to be -4 to 4. And the reason why I'm doing this is so that the graph is not squished, because the screen is not square. And now when I push graph,
oh my god, that's not what I got.
They have the butterfly one in textbook.
oh yeah,
Oh my god, it's so pretty though.
yep,
What was your function again?
function was 4
Oh, 4 cosine.
cosine 4 theta.
I put 4 cosine theta in and just got a circle. The function that they have for here is e to the sine theta minus 2 cosine 4 theta.
To make a butterfly?
Yeah.
Yeah, there are also formulas for hearts and things like that, so you can do a lot of cool stuff with this. All right, so now this is something that I really can't teach you. You have to explore. You have to obviously be interested first, and then sit there and play with a calculator or a graphing utility of your choice to figure out what's happening with this. I'm expecting you to know y equal mx plus b is the linear line. You've been learning that for last 4 years or 5 years of math, right? And then y equals x squared. y equals x cubed, y equals square root of x, y equals ln x, y equals e to the x, right? So you have spent years learning and memorizing graphs that are connected to your y equals functions, right? Is it possible for me to teach you all different shapes and functions you can get, including the butterfly and everything else, right, in 15 minutes? So you need to sit there and make some, so let's change now 4 into 2. So now you have 2 theta, and what you notice is now you have 4 petals instead of 8. And you said, okay, 4 theta gave me 8 petals, 2 theta gives me 4 petals. It seems that it's doubling up. Then you say, let me try what happens if I type in 5, and you are expecting what?
10.
And you will get, no, you will get 5.
Wait, what? Why?
Yeah, exactly.
Oh my God.
So what you learn from here is that odd number has that many petals, even number gets doubled. And now that's only on the cosine thing, right? Now if I go and switch cosine into sine and graph the same,
Because sine's an odd function.
then you see that it's still 5, which is great, but the picture is rotated now. So the picture rotates. Used to be on the centered on x-axis, right, with the cosine, and now with the sine is centered on y. In order to learn, get some feel for polar coordinates, get ready for that Calc 3 class, you have to spend hour, 2, 3 hours playing with this. What if, right? And don't be shy to say e to the sine theta and all of these kind of things, because, eventually, so what is e to the sine theta? What kind of graph is that going to produce? Yeah, to me it looks like some kind of oval. How about, if you add some stuff, plus cosine theta. I'm just making up anything. Right? So you get to play with these things and then try and figure out what you can. Let's try another one. Why? So clear all this. 2 sine theta close parenthesis minus 1. All right. Right? So playing with these, right, will take time. You are not going to be asked to memorize what these shapes are, but the more you know, the easier Calc 3 will go, because these will become bases for the objects that are built on top of it. You can do some really cool mechanical engineering. You can do a lot of 3D printing and a whole bunch of design when you know which way the polar coordinates work. And now, to push further with this stuff, I want to discuss the easiest, right, the cheapest functions that you can have in the polar world. And before we do that, I'm just going to quickly remind you, I'll put remember. So remember this situation from your algebra course where you had a line like right there going to point A, and you call that x equals A, and you had a horizontal line as one of the basic lines going to, let's say, point B, and you called it y equals B. So these are the cheapest lines that you can get in terms of also cheapest function, because a constant, right? Y equals a number. These are the cheapest you can get. And if you look at the red one, it has equation x equals to a number. And because x equals a number, it doesn't at all mention y in it. And y takes on all of the values. This is something going to be very important for you for Calc 3, because you will understand that if one of the variables doesn't show up in your equation out of x, y, and z, that means that in that axis, the object is going to be infinite. So we'll talk about that, obviously, in Calc 3 eventually. But now you see that your object, in this case the red line, stretches infinitely in the y direction, and y is not mentioned in the equation. Similarly, in blue, x is taking all of the values between negative infinity and positive infinity, and y is pinned to be a single number, so you just get a horizontal line through y. Now that's something that you guys did in algebra long time ago. They gave you rise to horizontal, vertical asymptotes, and so on. So now we are going to take a look what happens when I have the r and theta equal to a number, one at a time. So if I have r equal to a number, let's say r equals to a, what do I get?
Constant expansion. Because it would be on all points of all degrees.
Which one is changing all the time? Which one is standing still?
Your radius would be the same.
Radius will always be the same. And what changes?
Your angle.
My angle. Okay, so what would that make?
The circle.
A circle. Nice. So that's a circle with radius a. Remember how your equation was really annoying in xy coordinate system? It was x squared plus y squared equal a squared, right? Mm-hmm. Look at it now. R equals to 3. It's a circle with radius 3. So which one do you want to integrate? Do you want to integrate x squared plus y squared, right? Or you just want to integrate 3? Yeah, you want to integrate 3. So this is where we are making a point that these systems do not compete. One is great for one thing, the other one is great for the other thing, and they don't compete. And if you force them, you're going to get absolutely crazy expressions, and then good luck with them, right? So r equals a is a circle. That's one of the basic formulas, and it's really awesome. And how about theta equals a number? Excellent. Very important to know that it's line through the origin. And it's line through the origin like there. And this angle here is your angle B. Yes. So you have your, again, these are all happening in XY realm. So the basic functions here are circle and the line through the origin. Would you expect that line that goes away from the origin, would you expect it to have a simple or a complicated formula? Complicated. It will include secants.
About thirds.
That's why that's why we do not want to deal with lines unless they're going through the origin in polar coordinates. Will you have to? Yeah, here and there. But generally we stay away from them because you want to deal with the rounded objects. You saw the flower, you saw the circle. There is also a part that's called cardoid, which looks like a heart, right? The cardoid. So there are a whole bunch of shapes, and if you open the book and take a look at some of these shapes, right, it will be clear. None of them have sharp edges and corners like triangles and rectangles because polar coordinates like roundness, and that's what they're used for, which is why they bring rise to cylindrical, which is a cylinder, which is your Coke can, right? And they also give rise to what is called spherical coordinates. Sphere, that's a ball, also round, right? So polar coordinates are going to be reserved for the rounded objects, and the x, y rectangular coordinates for things that have shape like triangle and rectangle and so on. So again, they work together. Now, to further solidify this, we're going to take a look at y equals, let's say, 4 sine 2 theta as a function. Now you are getting a 4-petal flower, and because it's a 4-petal flower, you know that it is not a function. So if you are to graph this thing, you are going to get a petal right there, another one right there, another one right there. This sits in the xy coordinate system, but the polar coordinates are used to trace this flower. Is this a function? The answer is hell no, right? It fails vertical line test. It's not a function. So, we can't do derivatives and integrals and all of that stuff easily because calculus likes functions. And if you try to convert this into rectangular, why did I say y? It's r equals, there we go. It's r equals 4 sine theta. If you try to convert this into rectangular, you see the horror immediately. First, we're going to write it as r equals 8 sine theta cosine theta because the double angle formula identity, right? Sine of 2 theta is 2 sine cosine, and then 2 times 4 is 8. So now you have that. And then you convert, all of this stuff into rectangular. Your r is the square root of x squared plus y squared, then 8. Over here, it's much easier if you kind of cheat because x equals r cosine theta and y equals r sine theta. You can solve for cosine and sine as x over r and y over r, and you plug those in. That's easier than to go sine of inverse tangent and cosine of inverse tangent. You can, but it's more work. So we have x over r times y over r, and But we know r is the square root. So it's 8 xy over square root x squared plus y times another square root of x squared plus y squared. And that's great because they're just going to give you a single x squared plus y squared. Now you have the same one on the other side, so you can combine them into 3/2 exponent if you want. And look at this thing. This is your flower, right, with 4 petals in rectangular coordinates. You can't do anything, exactly. So it's this versus r equals 4 sine 2 theta. And you can immediately see the one on the right, joke to differentiate, joke to integrate, right? The one on the left, you just look at it and cry, right? So again, they do not compete. They complement each other. One helps with round, world of a round. The old one, right, it works with rectangle squares, triangles, and so on. So now that we established this, we understand, let's go all the way back to take a look one more time. We understand that the polar coordinates have coordinates r, theta, where r is the radius and theta is an angle. We understand that we are supposed to graph the point by drawing out the radius, whether it's positive or negative on x-axis, and then just swing that for the angle given with a diagram to graph any point that you can possibly run into. Got into conversions to show that the two systems, because they both exist on the xy, they both have a point, right, point to point correspondence, we can move back and forth, but generally we don't want to, because polar world is good for round and rectangular is good for edges. Polar function is now r equals f of theta. So theta is the input and r is the output. R equals 2 theta turned out to be a spiral. Technically, r equals a theta is a spiral. And if you want to densely pack your spiral, you know, don't go crazy with A. The two basic graphs we get are r equals a number, which always gives a circle with a radius, whatever the number was, and b equals a number, which is the line that goes through the origin. And we saw a couple of these graphs. I already did them on the calculator. And I am asking you to spend hours. If you're going to Calc 3, hours over the break, right? Right now, 1 to 2 hours to kind of see what you can get and play with these shapes. But over the break, if you're going to Calc 3 next semester, you need to get as proficient with this as possible so you don't get slain over there. And now we are ready to take a look at the calculus with polar coordinates. As a case. Or calculus in polar coordinates, how about that? And I'm going to start, obviously, with the derivative. And derivative says that, you know, you have r equals f of theta. You will differentiate in respect to theta. And you will get r prime is equal to f prime of theta. That is the same as if you had your y and x. So if I have r equals 4 sine 2 theta, and I wanted to find r prime, I will just have the regular derivative you learned from Calc 1, nothing special. The 4 cosine 2 theta times, very good for that 8, times the 2 from the chain rule creates 8 cosine 2 theta. So the derivatives are done exactly the same. And once we have the derivative, we can measure the change. Change of what? Change of position in time, which is called velocity. Change of velocity in time, which is called the acceleration. And now you can observe the particles or cats or something that are going in right circular path of some kind. You can observe their velocities, acceleration, and everything else, because now your input is in terms of theta, angular velocity. In Calc 1, I teach a problem with related rates, where we learn how to mathematically derive a function that would trace a rocket launch or something, and there's a lot of cool applications. One thing that we actually want to know in calculus, which is a central problem of Calculus 1, is the tangent line. Because the tangent line, the slope of the tangent line, measures instantaneous change. That's the speed you are ticketed for, right? Because that was the speed of the instant when you were measured. A whole bunch of other examples that are everywhere on what the derivatives are used. The issue that we have, guys, is that your tangent line is y equal mx plus b, because you do not want to go into dealing with lines away from the origin, right? And y equal mx plus b is pretty much always away from the origin. So now, somehow, I need to have the derivative dy dx expressed in terms of polar coordinates. And as soon as you hear the two worlds mixing, you know that is not going to be pretty, right? All right, let's go. Lock the doors. So I have a flower, let's say, and I want to know the tangent line there. Well, in order to come up with a tangent line, and tangent line is y equal mx plus b, good one, we need to calculate our slope. And a slope m is dy dx computed at x equals some number. Perfect. I don't have y, I don't have x's anymore. I'm not even computing at x equals to a, because the theta is now my input. So, as you can see, absolutely nothing is working for our good old easy tangent problem. Well, there is conversion. And the conversion says that x is equal to r cosine theta and y is equal to r sine theta. And if you differentiate in respect to theta, you will get derivative of r is going to be r prime, because remember r is a function of theta. Oh, I just can't fit here because both of these are product rules, right? Your r is a function of theta times cosine theta, and your r is a function of theta times sine theta. So if you need the derivatives of these, they are product rules. So you got to be careful about that. All right, so what is the trick? I need dy dx. And here is $1 million trick. Times 1 over d theta times 1 over d theta, because they actually cancel out, right? So you get dy d theta divided by dx d theta. So now, what is dy d theta? Well, that's the derivative in respect to theta of f of theta sine theta. Right? Because that's what y is. Y is f of theta times sine theta, and now I'm taking the derivative of it in respect to theta. And that is the product rule. Copy the first, derivative of the second, plus copy the second, and then derivative of the first is f prime. Dx d theta, same deal. We have the derivative in respect to theta of f of theta cosine theta. Copy the first times derivative of the second, that's negative sine theta, plus copy the second cosine theta, derivative of the first is f prime. So now, for my dy dx, I just need to divide these two. Dy dx is equal to, and now I'm going to just divide, but first I'm going to notice that there is a minus sign here, so I just want to write my derivatives first. So it's going to be f prime of theta sine theta plus f of theta cosine theta divided by f prime of theta cosine theta minus f of theta sine theta. This is your formula for the derivative. As you can see on the right-hand side, you are feeding thetas, and on the left-hand side, what you get back is dy dx, which is slope of the tangent line. A little bit convoluted, but possible to deal with. So what do? You now problem, find the tangent line for, let's say, r equals 4 sine 2 theta at theta equals, let's say, pi over 6. So try to grind through this on your own. You have this is your r is f of theta, right? R is f of theta. So you have your f of theta as 4 sine 2 theta. Get f prime, plug everything in, and then compute the slope to get m equals a number. Because eventually, once you plug all of that in, then each theta, you'll have like 17,000 of them. Each theta becomes pi over 6. And then you will be computing sines and cosines of pi over 6. And everything will collapse down to m equals a number, which becomes your slope. All right, no pressure. We have 18 seconds. Go. Okay, let's take a look at this together. Bring the power up. So we first find f prime of theta, which is 8 cosine 2 theta, and now we plug that dy dx. So 8 cosine 2 theta times sine theta plus 4 sine 2 theta times cosine theta divided by 8 cosine 2 theta cosine theta minus f is 4 sine 2 theta sine theta.
These look like the identities for sine and cosine. I can't remember what one.
Now plug in pi over 6. So slope m is 8 cosine pi over 3 sine pi over 6 plus 4 sine pi over 3 cosine pi over 6 divided by 8 cosine pi over 3 cosine pi over 6 minus 4 sine pi over 3 sine pi over 6. Woohoo. M equals cosine of pi over 3 is a half. 8 times 1/2 times 1/2 plus 4 times sine of pi over 3 is root 3 over 2, and cosine is also root 3 over 2. 8 times cosine of pi over 3, that's a half and a half. No lies. Cosine of pi over 3 is a half. Cosine of pi over 6 is root 3 over 2. Minus 4. Sine is root 3 over 2. And sine of pi over 6 is a half. Nice. So we have 4 plus 2 root 3 on top, because the 2 times 2 on the bottom is 4, cancels. Over here we have 4 root 3 minus root 3 for a total of 4 plus 2 root 3 divided by root 3. 3 root 3. And now we rationalize this because we don't like root 3 in the denominator.
Isn't it two root 3 on the bottom?
How? This is 4 root 3, right?
Yeah.
And this is
Shouldn't that just be 3 on top?
just root 3.
That's not 2 root 3?
2 times 2 is 4, and it cancels, right?
But you got root 3 times root 3. So shouldn't it just be 3 on top? Yeah. Thank you.
Oh, you're talking about this one.
Well, both of them. Because 4 times root 3 times 1 is 4 root 3. Divided by 2 would be 2 root 3. Yeah, 2 root 3 on the bottom, not 4.
Over here we have 2 root 3s.
Divided by 4.
Yeah. So this is 3 root 3 times 3 root 3. Root 3 times root 3 is root 9, which is 3. So it's just a 3. So this is just a 7 here, right? On the denominator, 8 cancels with these 2. You get a 2.
So yeah, 2 root 3 minus root 3.
So 2 root 3 minus root 3 is just root 3. And now we rationalize. Okay, much better. You win. I was just testing you all. Very good. Very good. Very good. 7 root 3 over 3. That's our slope. All this work to get a slope. Now that we have a slope, what do? We convert our point, right? Because we have r equals 4 sine 2 theta, and we have that theta is equal to pi over 6. So I can calculate r, 4 sine of pi over 3, which is 4 root 3 over 2, which is 2 root 3. I need that so that I can use r theta to convert into x and a y, because I already have a slope m, and when I have x, y, and m, I can find b. So we have a point pi over 6 and 2 root 3. X is equal to r cosine theta. That's 2 root 3 times cosine pi over 6, which is root 3, because cosine of pi over 6 is a half. Y equals r sine theta is 2 root 3 times root 3 over 2, because that's sine pi over 6, and it's just 3, right? So now I have a point of root 3, 3. So y equal mx plus b. Y is 3. Slope m is 7 root 3 over 3. X is root 3 plus b. These guys will cancel. And look at b. I'm getting negative 4. Root 3 times root 3 is 3, cancels with a 3 on the bottom. Right?
Oh, right, yeah, cancels, right. Yeah.
So root 3 times root 3 is root 9, which is 3. 3 cancels 3.
Oh,
And you have 3 minus 7, it's negative 4.
You're so right.
I was born that way. Except when I'm testing you on that.
Yeah, I appreciate that.
Then I'm purposely wrong. Y equals 7 root 3 over 3x minus 4. That's the tangent line at theta equals pi over 6. You change that pi over 6 into anything else, the whole calculation changes completely, right? Because you have to recompute the slope up there, you have to recompute everything, right?
So I'm guessing for the final, we're gonna have a couple of overcoordinate questions.
Yeah, 7 of these is good to go.
Are they gonna be neat, like, they're gonna be like pi over 6, pi over 3, pi half?
Everything will be very neat.
Okay.
You are only going to see 0, pi over 6, pi over 4, pi over 3, pi over 2. Those are reference angles.
Various mutations of them.
Why? Well, I guess
Don't give him ideas.
No, I'm just going to give him a special exam. It's fine. Now, what are you expecting? Well, guys, we still have to do integration. So far we covered this. So what are you expecting on your exam? I said 3 questions from chapter 12. That's not featured on any of your exams. 12.1, parametric. You have graphing parametric equations or converting parametric equations, right? That's the 2 things, right? Along with orientation, right? Which way the arrows move, right? The flow of the graph. So that's and now 12.2 is what we did prior to this, which is either graphing polar coordinates, graphing a point, graphing a function, where you pick the values for theta and you compute, or convert between x and y domain, which is actually very important for your You know which problem this is relevant for 12.2 still? Wish I included this. You are going to see in your Calc 3 formula for these guys, right? That's going to be in Calc 3. And it's going to be called elliptical paraboloid, but most of the time it will have a circle. So something like this in the Calc 3 with the z-axis and the x-axis and the y-axis will be called elliptical paraboloid, and this one in particular could have a z equals, let's say, 3x squared plus 3y squared, right? You have this. So that would be a rectangular equation. Your job will be to write it as a z equals 3 times r squared. You see that? When you factor out 3 together, you get x squared plus y squared, and that's going to be the polar base. So from here to here, it's a polar base. And then when you add z to it, you get what we call cylindrical coordinates. Your ability to convert between the systems is going to be very important on Calc 3. So this one over here is just that you know that the conversion for a circle, because it is a circular base. If you move this one to be 3 and this one to be 5, then it's ellipse. So squished in that case, which is why it's called elliptical paraboloid, even when it's a circle, because circle is a special ellipse. Ellipse is the boss shape. So just like rectangle and square. Rectangle is the boss shape, and square is a special case where all sides are the same. Circle is also a special case of ellipse. Ellipse is the boss shape, and when the A and B radius from ellipse happen to be the same, then you get a circle. So when the numbers are the same, you get a circle. When the numbers are different, you get. You also seen that also in your parametric equations. We had x equals. You remember your equation was for parametric? R equals. Do you remember it?
No.
R equal, yeah, parametric. It was x equals r cosine t and y equal r sine t. And then when they are A and B, you get ellipse. You remember those? Now I'm just gonna point my finger there. Right? We have t's over here. Now I have thetas for conversion. But it's this r that goes around that makes a circle. Same r. Anyway, cool. So now we understand a whole bunch of stuff. As my voice is starting to degrade, we need to talk about integration. And integration is the last part of the lecture and the last part of Calculus 2. So in integration, you always have independent variable, which is the variable you are integrating in respect to. It was always within a d part, dx or dy. You always had that before. And you know that if you are integrating in respect to x, then you have those vertical representative rectangles, and they are dx width. And if you had the horizontal ones, it was dy. Well, now we are moving away from dx and dy. We're going into the polar domain, and we are talking about what will be known as representative pizza slice d theta. So for integration, to find area we'll have 1/2 integral alpha to beta, because those are angles now. We don't have a and b, right? We have alpha and beta because we are dealing with angles. And now we have our f of theta squared d theta. So this is the integral that we are dealing with in polar coordinates to find the area. Now, there's a whole proof and a thing in a book, why is there 1/2? So I don't want to dwell on that too much. What I want to dwell upon is that alpha and beta are angles in terms of pi, right, in radians. And alpha and beta in that final calculation, when you have f of b minus f of a, alpha and beta are the ones that bring pi to the party, right? So if alpha and beta are angles and they bring pi to the party, and this one over here is function squared, and we know function is r squared. Do we all see a circle there?
Kind of like triangles.
No triangles. I just said r squared pi. It's a circle. So let's take a look at some cool features of integration in polar coordinates. First off is area of the circle. And this is actually a proof, because I'm going to say that radius, the function, right, is capital R. So you can do r equals 3, r equals whatever number, but I'm going to just use it with a capital R for all of them. And I want the full circle, which means on 0 to 2 pi. That's the full circle. Can I just eat a pizza slice? Yeah, that would be 0 to pi over 4, right? Pizza slice.
Why would you do pi over 2?
That's 2 pizza slices. So pi over 2 is on top, right? So you have 2 pizza slices to pi over 2. Pi over 4 is 1 pizza slice right here. But I want a whole pie. The way I deal with pizza is I take the whole pie, I fold it in half, and I eat it. So.
Sounds amazing.
You make the pizza top, you just glob a giant spoonful of mayo in between it.
Ah.
Well, that's clear. You have to. But generally, people start bitching when I say that I put mayo on pizza. So. I usually don't mention it, but yeah, I would never eat pizza without mayo.
No, I don't put mayo on pizza.
I would never.
You
use it in place of cheese, or you just add it to it?
I just add it to it. It's just the thing that it's missing. It's not.
Or you just like the flavor of it?
I'm Slav, which means I eat everything other than cake with mayo. Fries, burgers. I don't put it on steak. I could. So.
I met someone else that does that, and I can't think of who it is, but I was talking
Whoever it
about
is,
that.
is a true Slav. There are 2 things: mayo and Slav squat. That's it. That's the only thing. Mayo and Slav.
The main mayonnaise, or you add other things to it?
Plain is just fine. You don't need anything else. It makes 90% of everything awesome. Yeah, I showed up at a department party on Thursday with my own personal mayo. So everyone was like, "What the hell is going on?" I said, "Look how many noob sandwiches you have over here."
Oh my god, awesome.
I should try that.
All right, so area of the circle. This is very important. This thing over here says whole circle, because I can work with wedges, with pizza slices, right? I can cut a quarter of a circle or a half of a circle. 0 to pi is half of the circle, right? But I want the area of the whole thing. That's why it's going to be 0 to 2 pi, full circle. So now, if I want to find the area, oops, not need to be dramatic. Area is going to be 1/2 integral 0 to 2 pi of, and my function f of theta is just r, and I need to square that, and then I have d theta. So now before you go nuclear, just remember that r squared is what? R is a number. That's you know the equation of a circle is like r equals to 3, right? So r is 3, and then it's 3 squared is 9, right? So when I integrate this, I'm just getting r squared theta computed from 0 to 2 pi. This is going to be 1/2 r squared 2 pi minus 0, which is pi r squared, which is what your equation for the area of the circle is. So next time you're tutoring someone, 7th grade or whatever, what was the area of the circle? Pi r squared. Why? Say no more. You now know the proof. All right? I gotta explain a couple of years of math in between, but again, not a problem for you experienced tutors.
I'm just, why wouldn't the r squared become r cubed over 3?
We are integrating in respect to theta.
Right.
R is a number.
So r does not get.
R is constant, yeah. It's not dr, it's d theta. Theta is a variable.
Oh, okay. And then you're
So you just copy it. You can kick this r squared. If you want, you can kick this r squared outside of the integral. It's not a variable.
Oh.
It's a constant.
So only if there's a theta in line with your equation.
That's the next example.
Oh, no.
Say no more. We want to see what's the area of that flower we've been talking about for so long. Area of the flower r equals 4 sine 2. I think we beat this example to death. We had this example for graphing, we had this example for conversion, we had this example for derivative of tangent line, and now we have it for the area. So you absolutely are getting a PhD in this example. And I want the whole flower, which means 0 to 2 pi. I'll write it in blood. Whole flower, which is 0 to 2 pi. All right. So now we have area is 1/2, and now whole flower 0 to 2 pi, and we have our 4 sine 2 theta squared d theta. Do we all see what's coming up? I hope you see sine squared coming up.
Oh, yeah.
And how do we integrate sine squared?
Oh, it's 1 minus cosine.
That one.
2.
That one.
Need that one.
The only way you can do this. That's it. All right, so what's 4 squared?
16.
Kick it outside. Very good. And now, so we have 8 in front of the integral. And we have sine squared 2 theta d theta. Now we have our formula. 1 minus cosine 4 theta divided by 2. The formula, the power reducing formula, doubles whatever angle you have. We are starting with a 2 theta, Therefore, the formula will give you 4 theta back. It doubles whatever you have. So now, 8 divided by 2 is 4. Integral in parentheses 1 minus cosine 4 theta d theta from 0 to 2 pi. What do we have? 4, and the integral here is theta minus over 4, very good, from 0 to 2 pi.
4 theta minus sine 4 theta.
Now what happens when I plug in 0 for sine and when I plug in 2 pi for sine?
The 0 eats away and 2 pi becomes
8 pi, and sine of 8 pi is 0. It's always 0 at the node. Yep. So we have 4, 2 pi minus sine 8 pi divided by 4 minus 0 plus sine of 0 over 4.
And that was your challenge question on lab 2. Why a pi or a2 pi will always be 0, or the sine of a2 pi would always be 0.
Yeah. Good. So now you have the full calculation here. Now, what if I asked you what is the area of a single petal?
Since there's 4 petals, just divide by 4.
Divide this answer by 4. Now, you have to be very careful with these problems, guys. The issue that you are going to have now is that you have no experience with graphs. That one is a killer for you. And here's why. Some of you will quickly catch up on the idea, if I can do a quarter of a circle, integrating from 0 to pi over 2, then I can do 1 out of 4 petals of the flower, 0 to pi over 2. Halfway true. Because sine 1, right? When you draw the sine graph is traced the full petal from 0 to pi over 2, and then it moves to the next petal. But when you are graphing cosine, it doesn't work that way. So if this problem was a cosine problem, it still graphs the flower, which is turned, but when it starts tracing the cosine, it traces the half of. Okay, I'm going to draw what I'm talking about, because it will not make sense if I just trace it in the air. All right, so 4 sine 2 theta is a flower that has petals like this. And that is 0 to 2 pi flower. If you want to trace one petal for a sine flower, it's like this, and it's 0 to pi over 2. And this is what you would like to happen all the time. It doesn't. It doesn't. Because for r equals, for cosine 2 theta, we'll have your flower this way, centered on the axis from 0 to 2 pi. And you know what's traced from 0 to pi over 2?
Oh, happening 2 of them.
Exactly. It starts here, and it traces half of this one, and it traces half of that one, and stops there. That's how annoying these things can be. So if you want to, be a smart cookie and integrate to find the area of a single petal, messing with the limits,
You have to break it up into 3 different limits.
you have to use it. Well, you have to do negative pi over 4 to pi over 4 to come up with for the cosine, and it's not easy. So the best part for these flower things is for you to get the whole thing from 0 to 2 pi, because that will definitely give you the whole flower, and then divide it by the number of panels you have. So that's the basic integration. If I want area of the single pizza slice, what's the radius of the pizza? Diameter is 16, right? So radius is 8? 16-inch pizza? That's diameter, right? So R equals 8-inch pizza, right? That's our circle. Radius 8, diameter 16. Area of the single pizza slice. Okay, we can draw the pie. And the single slice of pizza right there. And that's 0 to pi over 4. Because you have pi over 2 on top, and then 3 pi over 4, and then pi, and then all the way to 2 pi on the other side. So now we can calculate 1/2 integral of 0 to pi over 4, and you have your 8 squared d theta. That's a 64 theta cut in half is 32 theta from 0 to pi over 4, and then 32 times pi over 4 minus 0, which is 8 pi inches squared. So now you know what to ask for next time you're at a place. Which is why my wife doesn't take me anywhere. I have 24 pi inches squared of pizza.
Taking this class makes me regret that Action Park is closed down forever. That'd be a great calculus field trip. Determine whether or not you'll die on this ride.
Oh my god.
Action Park. Class Action Park.
I don't know what that is.
It was up in New Year's Eve. It was where Mountain Creek was, not Mountain Creek, one of the mountains. It used to be a ski resort, but in the summer it was a water park that had fully designed.
Yeah, Mountain Creek.
It was Mountain Creek?
Mountain Creek was ski resort water park. I'm pretty sure it's up there.
Maybe you can still go there. There's no electricity, probably. But how about?
Wait, I have a question.
Yes.
Why don't you have to multiply that by 8 again? Like, because like.
Well, I didn't ask for a whole pizza. I asked for a single slice. There's the word single.
Okay.
Now, you know, I mean, I never worked in pizzeria, but I've been pizzeria here and there, they, you know, when you have the person, it's like, can I have a slice of pizza? And the worker goes, grab a slice. No, can I have that one, right? So let's say they want this slice over here. Well, it's still 8 pi. Your limits are 5 pi over 4 to 3 pi over 2, right? This pizza slice, 5 pi over 4 to 3 pi over 2. It gives you the same area because it's the same size. It's just that, same area, same size. Just different limits. All right, cool. But enough of these basic things. We all know that we can intersect circle with a flower and flower with the cardioid and cardioid with the circle and look for the different areas that they would cut off in between, which is where the fun begins and Calc2 ends. Say you have a flower that extends all the way out to 2, and this is going to be a cosine 1 because it sits on axis. So this line here is r equals 2 cosine 2 theta. And now you're going to say how and why. Well, this 2 is that 2 because it stretches out from the origin to 2. And this 2 is a fact that it has 4 petals. Right? And it's cosine because it sits on x-axis. Remember how sine was offset at the 45? I promise I wasn't born knowing this. I saw it at one point for the first time, and then I just played on the calculator until I killed the batteries. That's the and at that point there was no computer graphics to, do these kind of things. So, no, I had the TI-83. So, all of the features of the formula, this is how I know what it is. So I have that flower there, and now I'm going to put a circle with the radius 1, which will obviously have some stuff poking out, right? So here's a circle, and that one is r equals to 1. There's so many cool things we can compute. But let's compute the obvious. How much is this? What's the area of that one part?
2 cos 2 theta squared minus
Perfect. Yes.
yeah, just area.
It's the same as the area between two curves where you have far away minus close by. We just need to be careful with limits of integration.
Do you have to split these into 2 integrals?
No.
You don't have to for polar?
No. You didn't have to split the other ones either. Unless they change which one is on top, which was on the bottom.
Yeah.
Yeah. This one, yeah. You would have to switch that if you want to find, these areas inside and stuff like that. I agree. For this one, you don't have to switch. All right, so area is 1/2 alpha beta f squared minus g squared d theta. When you have two curves, it's the same as your, remember 6.2? Our first lecture started with this formula in XY coordinate system. We are ending the course with this formula for R. It has squares now because the main formula has a square. So in some sense, we went the full circle. Every pun intended, okay? Every single one. All right.
So you're doing the arc length of polar curve too?
No, that's it. We're done with this. Sorry, disappointed. Now, the biggest issue we have here are these limits, alpha and beta, and you have to find them when you set two equations equal to each other, and this time you are solving trigonometric equations, instead of solving what you had earlier with x squared and blah blah. So now, to find these alpha beta limits, set two equations equal, and in our case 2 cosine 2 theta is equal to 1. That would be cosine 2 theta is equal to 1/2. And we know that cosine is equal to 1/2 when we have pi over 3, right? So from here, 2 theta is equal to pi over 3. I can say in parentheses because cosine of pi over 3 is 1/2. So now we have 2 theta is equal to pi over 3, theta is equal to pi over 6, and immediately, if you look at the picture for about a third of a second, you would see that the other one is negative pi over 6, right? Because there is a limit right there. Do we all see the purple lines I drew? Here's your alpha angle, here's your beta angle.
In this case, would we be able to say that there's symmetry at one of the pi over 6s?
Yes,
Okay.
because it's the even equation.